define the neostatic on a horizontal plane using the force sensor.
By dividing the applied force over the normal force. The applied force, which the sensor gives us, and the normal force, which is the weight of this block, and some extra weights. Before we start, we have measured the mass of this block to be 131 grams, and we have here the weight, which is 250 grams.
For sure, we will put in our consideration before doing our calculations. We will multiply it by 9.8 to turn it into newtons. Then I will illustrate more about the tools we need. We have the dynamic track motion, force sensor, wooden part, and wooden surface, the external body weight, interface, and the laptop. Pascal application to display us the digital data the force sensor will give us, and my friend Harvey will show us how to set the application.
Before we start, we should make sure that the force is connected to Pascal. Here we have the icon, which is hardware setup. We can choose it. If we find this, this means that the sensor is connected to the Pascal. And then we have to change the sign because the force sensor taking the results in negative sign. So we have to change it to positive. And then we click up. And now we would choose this icon. Here in the half of the screen we should choose graph, and on the other side we should choose video analysis. And then we have three options. We should choose the third option. And then we are going to set up our graph. On the y-axis we choose force in Newton, and on the x-axis it shows time per second. Okay, and now we are going to set up the graph. We don't need the negative signs, so we are going to put it in zeros. Now we can start our first trial. But before we start, we must make sure that the sensor is on zero. We are going to click this button to make sure it is on zero.
We will add 150 grams at first and start recording for sure. Then we will start pulling the force sensor. We got readings right here. We press the stop button. And here we got our first trial results.
Yeah.
We will choose the highest point by clicking run home,
which is this point. Then, after the fourth trial, we are going to get this coordinate, but now we are going to make the second trial.
Don't forget to press recording again, but first of all we will add another external weight. Now it became 500 grams plus the weight of the wooden part.
Here we have another graph, round 2. We have to choose the highest point in the graph here, and then now we can start to
Record
trial 3.
The first trial we will add more external weight, so we will find that the weight we added now total equals 750 grams, plus for sure the weight of the wooden part. We shouldn't forget about it. We will press zero, add the force sensor, start recording, and pulling our force sensor. Stop recording. Here's the last trial. We will add wooden our weight. The result will be 1 kilogram plus the wooden more weight. Don't forget to make it zero again. Start recording. Now we can see that we finished all our 4 trials, and we will get the reading of the highest point, take the average, and find out more static.
Here we can get our round from this icon. We have run 1, which is the. We can drag the coordinate by this icon here, show this icon, as you can see, the coordinates appear to us. If we drag it to the highest point in the graph, we can get that it is about
1.2 newtons. Switch to the next one to take our next coordinates.
1,
The highest point, as we have said previously,
2, at coordinates. We can find it to be 1.7 Newton. Here we have the circuit drive, and now we are going to switch to the circuit drive and take the highest point in the graph here. We are going to take the coordinates of the highest point. We'll find it to be 2.1 meters. Try 4 at coordinates. We can find it to be 2.1. Here we have the readings for the applied force, and here we have the normal force. First, we have measured to be 131 grams. We will change it to kilograms, which is be about 0.131 kilograms, and adding the weight of this extra weight, and then times it to 9.8 to get the normal force. And then we are going to divide the applied force for each read to the normal force and get the average of the mu statics to get a one final mu static,
which will be the most accurate one for real mu static. As we have calculated previously the mu static on horizontal plane using 4 trials and getting their average and creating out the error percent, we will do the experiment again, but on a plane with an inclination.
As we know, when the body is about to move and without any external forces, the angle of inclination equals the angle of friction. And we know that the mu static equals the tan of the angle of friction. So now
we will start rising our dynamic motion track gradually until we find our body is about to move. It starts moving at an angle of 16 degrees.
So here we can take it by select 10 and it's 16. We find it to be 0.28.
Now we're going to calculate the mu static by using the applied force we have already got from the readings of the graph. The first reading was 1.2. We will divide it over the normal force. The normal force will be the weight of the wooden bar, 0.131 kilograms plus 0.25 times 9.8 to switch it into newtons. We will find it to be 3.7 newtons. The next reading, we got 1.7 newtons at the applied force, and the normal force we will add again 0.131 plus 0.5. As we added in the second trial another bar, multiply 9.8, we will find it 6.18 newtons. The third trial we find the applied force 2.1. The normal force is 0.131 plus 0.75 times 99.8, resulting on 2 newtons 8.6. The last trial we find the applied force to be 2.2. The normal force 0.131 plus 1 kilogram, as we at the last trial there was 4 bars, each 250 grams, then the total will be 1 kilogram, times 9.8, resulting in newtons 11.1.
And then we are going to the coefficient, the mu static, or the coefficient of limiting fraction force. We are going to divide the applied force over the normal force. Here we have the first applied force to be 1.2 Newton and the normal force to be 3.7 Newton. If we divide them, we find it to be 0.32. And for the second trial, we have the applied force to be 1.7 Newton and the normal force 6.18 Newton. And it gives us mu static of 0.27. In the third trial, we divide 2.1, the applied force, over the normal force, which is 8.6, to give us mu static of 0.24. And in the first trial and the last one, we have applied force of 2.2 Newton and normal force of 11.1. By dividing them, we have 0.2 mu static. To find the average of the first trial to be accurate, we add 0.32 plus 0.27 plus 0.24 plus 0.2 over 4. If we calculate them, we find it to be approximately 0.26. And as we have measured tan theta, or the tan of the friction angle, to be 0.28, which is the accurate reading, we can find the error ratio by dividing by minus the real reading from the average reading and divide it by the real reading. Here we have the real reading to be 0.28 minus the average reading, which is 0.26 over the real one, which is 0.28. By calculating it, we find it to have a ratio of error 0.07. Thank you for watching and hope you enjoyed.